So let us try to find out the value of modulus of z1 plus z2 squared. So as per property number 4, this can be written as z1 plus z2 multiplied to the conjugate of sum of z1 and z2. So I'm writing here, since mod of z square is equals to z times its conjugate, which will give us z1 plus z2 multiplied to, now we apply the property of the conjugate, which so given to complex number z1 and z2, and we add them and take the conjugate, that's equal to the sum of the conjugates. So this can be written as z1 bar plus z2 bar. Now we multiply them, so we have z1 multiplied to z1 bar plus z2 bar plus z2 multiplied to z1 bar plus z2 bar. When we distribute z1 to z1 bar plus z2 bar, we get z1 times z1 bar plus z1 times z2 bar plus z1 bar times z2 plus z2 bar. Now we again apply the formula that z1 times z1 bar will be simply equals to the absolute value of z1 squared, plus then we apply the same property to the fourth term, so that should give us the absolute value of z2 squared, leaving us with z1 times z2 bar. Now the third term, z1 bar plus z2, can be rewritten as the conjugate of z1 times z2 bar. That's because since the conjugate of z1 z2 bar is simply equals to z1 bar times z2 conjugate of its conjugate, which is equivalent to z1 bar times z2. Now we apply the property that given a complex number z, when we add it to its conjugate, it simply gives us 2 times the real part of z. And therefore we have the addition of the third and the fourth term will give us 2 times real part of z1 times z2 bar. So that proves the given theorem. Theorem number 8. So we begin from the left hand side. Here we have z1 minus z2, the absolute value squared, which can be rewritten as z1 minus z2 times z1 minus z2 bar. So we apply the same property that the mod of z squared is equals to z times its conjugate. So we have z1 minus z2 multiplied to z1 bar minus z2 bar. So here we're applying the property of conjugates. That gives us z1 times z1 bar minus z1 times z2 bar minus of z1 bar times z2 plus z2 times z2 bar, which is equals to mod of z1 squared plus mod of z2 squared minus, we can take minus negative 1 as the common factor, we have z1 times z2 bar plus z1 bar times z2, which is equals to mod z1 squared plus mod z2 squared minus z1 bar times z2 bar plus the z1 bar times z2 can be rewritten as z1 times z2 bar, and then we take its conjugate, since z1 times z2 bar, its conjugate is equals to z1 bar times z2, or vice versa. Here we can write that z1, yeah. So this is it. So now that gives us z1 squared plus z2 squared minus, so we are adding a complex number given by z1 plus z2 bar and adding it to its conjugate, so that should give us 2 times the real part of z1 times z2 bar. So this is the proof on the right hand side. So in this particular theorem, we have to prove that the modulus of the sum of two complex numbers z1 and z2 never exceeds the sum of their moduli, and it exceeds the difference of the moduli. So this is what we have to prove. So in order to prove this, let us begin with theorem number 7, which states that given the sum of two complex numbers, then the square of the absolute value is equals to the absolute value of z1 squared plus the absolute value of z2 squared plus 2 times the real part of the product of z1 and the conjugate of z2. So let this be equation number 1. So this was from theorem number 7. Also, we have for complex number z, we know that the real part of the complex number z is always lesser than or equals to the absolute value of the complex number and greater than or equals to the negative absolute value of the complex number. So if we use this, then we can write that the real part of the complex number z1 times z2 bar is always going to be lesser than or equals to the absolute value of z1 times z2 bar and greater than or equals to the negative of z1 times z2 bar. Now that we have this, now we can rewrite it as negative z1 more absolute value of z1 multiplied to the absolute value of z2 bar. Since given two complex numbers z1 and z2, if we take the absolute value of their product, then this is simply equals to the product of the moduli. So we have real part z1 times z2 bar is less than or equals to mod z1 multiplied to mod z2 bar. But we know that the absolute value of the conjugate of a complex number is equals to the absolute value of the complex number itself. That is, the absolute value of the conjugate of a complex number is equals to the absolute value of the same complex number. So we have the real part of z1 times z2 bar is less than or equals to the absolute value of z1 multiplied to the absolute value of z2. Now we are going to multiply it throughout by 2. Now this 2 being a positive real number, so the sign of the inequality will not get affected. Now in the next phase, we are going to add the absolute value of z1 squared plus absolute value of z2 squared throughout the inequality, and that should give us negative 2 z1 mod z2 is less than or equals to absolute value of z1 squared plus absolute value of z2 squared plus 2 times the real part of z1 times z2 bar less than or equals to z1 squared plus z2 squared plus 2 times absolute value of z1 multiplied to absolute value of z2. Now this is an identity, a minus b whole squared, so we can rewrite it as z1 absolute value of z1 minus absolute value of z2 whole squared is less than or equals to, this is from theorem number 7, which we can replace it as the sum of the modulus of the sum of the two complex numbers squared, which is less than equals to mod z1 plus mod z2 whole squared. Now we're going to take a positive square root on both sides, and that would simply give us the difference of the two complex number is less than or equals to the absolute value of the sum of the two complex number, and this value never exceeds the sum of the moduli. So this proves theorem number 9. Let's go to the next theorem. So in this particular theorem, we have the absolute value of the difference of two complex numbers can never be less than the difference of their moduli, and it is always less than the sum of their moduli. So in order to prove this particular theorem, we are going to take the help of theorem number 8, which states that the square of the absolute value of the difference of two complex number is always equals to mod z1 squared plus mod z2 squared minus 2 times the real part of z1 times z2 conjugate. So this is theorem number 8. So let us use this. Now we know that the real part of z1 times z2 bar is always lesser than or equals to the absolute value of the complex number z1 z2 bar, and is greater than or equals to the negative absolute value of z1 z2 bar. This comes from the fact that real part of z is always lesser than the absolute value of z and is greater than the negative absolute value of z. Now we can use the property of modulus, so that would be absolute value of z1 multiplied to absolute value of the conjugate of z2, which will be equals to the real part of z1 times z2 bar, which is less than or equals to the absolute value of z1 multiplied to the absolute value of the conjugate of z2. Now we have z1 multiplied absolute value of z1 multiplied to the absolute value of z2. Again, since the absolute value of the conjugate of a complex number is equal to the absolute value of the complex number itself, so we have real part of z1 times z2 bar is less than or equals to absolute value of z1 multiplied to absolute value of z2. Now we're going to multiply throughout by 2, and like in the previous theorem, we are going to add mod z1 squared plus mod z2 squared to each of the terms. So we have mod z1 squared plus mod z2 squared added to it, plus mod z1 squared plus mod z2 squared. So that should give us mod z1 minus mod z2 whole squared is less than or equal to, this is the theorem number 8, so which is simply z1 minus z2 absolute value squared is less than z1 plus z2 whole squared. Then we take the square root, absolute value of z1 minus absolute value of z2 is less than or equals to z1 minus z2 absolute value, the difference of the two complex number, it's always less than or equals to the sum of the absolute value of the complex numbers. So this is the proof of theorem number 10. Now from theorem number 9, we have for two complex numbers z1 and z2, the absolute value of the sum of the two complex number is always lesser than the sum of their absolute values. Now if we can extend it to three complex numbers. So if we have three complex numbers z1, z2 and z3, then we have the absolute value of the sum of the three complex number, which is z1 plus z2 plus z3. This can be rewritten as then we're going to add z1 and z2 and consider it as the first term, add it to the second term, which will be simply z3. And as per the above definition, or theorem number 9, we have this value is always lesser than the absolute value of z1 plus z2 plus the absolute value of z3. Now we can apply, so we have z1 plus z2 plus z3 is less than or equals to absolute value of z1 plus z2 plus absolute value of z3. Now the absolute value of the sum of z1 and z2 is further lesser than absolute value of z1 plus absolute value of z2 and the remaining z3. So finally we can say that the absolute value of sum of the three complex number is always lesser than the sum of their absolute values. Now if we extend it to n numbers of complex number, say for z1, z2 going all the way up to zn, then we can say that absolute value of sum of the complex numbers is never going to exceed the sum of the modulus. So we have all the way up to z of n. So by the method of induction, we can say that the absolute value of summation k going from 1 to n z of k, the absolute value is always less than summation the absolute value of complex number z with index k, where k runs from 1 to n.